So let's start by figuring out, are all the horses in the world white? And if not, then what's wrong with this proof? When I first heard this puzzle, back in my high school, my teacher gave it to me. I spent several days thinking either I'm crazy or the math is crazy. The math cannot be crazy, what's going on? Well, the math is not crazy, but there is a subtlety here, which is kind of not really obvious when you read it because it all makes sense. But once you have a little bit of experience doing induction proof yourself, you start noticing things like that. That said, even famous mathematicians sometimes have bugs in their induction proofs, so watch out for those. So, what goes wrong in this particular proof? Base case P of 0, that's fine. Induction hypothesis, assuming the predicate for arbitrary k, that looks fine. So let's look at the induction step. So let's take a set of k plus 1 horses and take one horse out. That's fine. We are left with k horses and we can apply the induction hypothesis to them. All of them are white. Now, the next line says put that horse back in and take out another horse. And this is where the subtlety comes in. Another horse. When we had our base case, there were no horses in the set. Particularly, there was no another horse. So in order to prove a base case for which you could make the sentence, take out one horse and take out another horse, we would have to prove it for k equals 1 and k equals 2. But for k equals 1, it already breaks down because for k equals 1, there is no another horse. So this is where there is a subtle bug in this proof. This is why the whole thing doesn't work out. It's not quite the induction itself, but that subtle assumption that's being made in the induction step that k must be at least 2. Well, k may be 1 and k may be 0. And then the things break down. So this is the kind of thing to watch for when you're doing induction proofs yourself. Make sure that whenever you're making your assumption, you're not using more than you actually assumed. Okay, so now let's try to generalize mathematical induction principle a little to make things a little bit more smooth. Sometimes you don't want to prove some statement starting with 0. You want to prove a statement starting with some other number. For example, if you're talking about prime numbers, it only makes sense to talk about numbers from 2 and up, and we'll see some other examples of that. Well, no problem, because we could always make a bijection between a countable set and natural numbers. In particular, we could make a bijection between set of numbers starting with any natural number a and natural numbers. And what it says is that we could actually assume start with any number, natural number a for our base case, and then just look at all the numbers that are greater than a for our induction step and induction hypothesis. And the reason it works is just because this is the same as proving induction on some n prime, which is equal to n minus a. Well, the n prime will start at 0. We are just kind of shortcutting and combining those two things together. Just say our base case starts at a. And in general, this works for all sorts of countable sets. Induction works not only for natural numbers. You could do induction on strings, you could do induction on pairs of things, on all sorts of things. And again, the reason for that is the same. If you have a bijection from natural numbers, say, to your set, then between natural numbers and your set, then all you need to do is to apply your predicate to whatever the output of that bijection is on a natural number k, or whatever it is. And then everything works. So let's do an example with changing the... Okay, so let's do a proof that starts with a base case other than 0. We will prove that for all n greater than or equal to 4, 2 to the n greater than or equal than n squared. So we will start by saying what our predicate is. It's an inequality. Either the left side is greater than or equal to the right side, or it's not. And the left side is 2 to the n, and the right side is n squared. So our predicate is 2 to the n is greater than or equal to n squared. The base case is for n equals 4. So P of 4 says that 2 to the 4 is greater than or equal than 4 squared. And indeed 2 to the 4 is equal to 16, which is greater than or equal, or actually equal to 4 squared. So the predicate P of 4 holds. For induction hypothesis, let's assume that for some arbitrary k, which is again greater than or equal to 4, 2 to the k greater than or equal to k squared. And for induction step, we will show that P of k implies P of k plus 1. That is, from 2 to the k greater than or equal to k squared, we can derive that 2 to the k plus 1 is greater than or equal to k plus 1 squared. Once we've done that, we could conclude by induction that for every n greater than or equal to 4, 2 to the n is at least n squared. So usually when you have induction proofs of such mathematical equalities or inequalities, you will start with either left-hand side or right-hand side and try to sort of extract the respectively left or right-hand side of the induction hypothesis from it. So in this case, we will start with 2 to the k plus 1 and we'll try to extract 2 to the k from there. And it's not that difficult because 2 to the k plus 1 is 2 times 2 to the k, which we can even write as 2 to the k plus 2 to the k. Now, by induction hypothesis, each of those 2 to the k's is greater than or equal to k squared. So 2 to the k plus 2 to the k is greater than or equal to k squared plus k squared. By the way, I could have written just 2 to the k is greater than or equal than 2 times k squared, and that would be totally fine. It just this way makes it slightly easier for the next step. So what we want to show now is that k squared plus k squared is greater than or equal to the right hand side of the expression in P of k plus 1. So k squared plus k squared is greater than or equal than k plus 1 squared. So let's write out k plus 1 squared. It will be k squared plus 2k plus 1. So one of the k squared in k squared plus 2k plus 1 matches the k squared in k squared plus k squared. So all that remains is to show that k squared is greater than or equal to k plus 1. So we will show it as kind of a little lemma on the side. Take the inequality k squared greater than or equal to k plus 1. Divide both sides by k. Well, k is positive. You end up with something that preserves the direction of inequality. Now, we want to show that k is greater than or equal to plus 1 over k. But remember that k is at least 4. So 1 over k is less than 1. So 2 plus 1 over k is less than 3. And well, 4 is less than 4 is greater than 3. And we are done showing that k squared greater than or equal to 2k plus 1. Now, with this, all that remains is to write out the whole thing. Well, we're pretty much done with the proof by now. So the last line is sort of a recap of what we've done before. 2 to the k plus 1 is 2 to the k plus 2 to the k. By induction hypothesis, this is greater than or equal to k squared plus k squared. And by this little lemma that we just did, is greater than or equal than k squared plus 2k plus 1, which was exactly k plus 1 squared. So we've shown that 2 to k plus 1 is greater than or equal to k plus 1 squared, which is exactly what we wanted. And now we can conclude that by induction, for all n greater than or equal to 4, 2 to the n is greater than or equal to n squared. This statement has an interesting application in computer science. Imagine that you have, let's say, some kind of database which has n elements in it, and you need to do some operation on this database, maybe a search, maybe something else. And suppose you have two algorithms. One runs in time number of elements in the database squared, and another one runs in a time 2 to the number of elements in the database. Which algorithm would be better to use? Well, if your n is equal to 3, then you might try the algorithm which is 2 to the n time. But if your n is anything reasonably large, you will know that your n squared algorithm will do much better than 2 to the n algorithm. So this induction proof that tells you that n squared is always less than or equal than 2 to the n would tell you that the algorithm running in time n squared will always outperform as n grows an algorithm running in time 2 to the n. We will talk a little bit more about running times of the algorithm in a few lectures. So let's try to do one more proof by induction, and that's again a proof that you've seen before. We are back to our puzzle about coins and what would have happened if instead of getting rid of a penny, Canada would introduce a 3-cent coin. So remember the statement that we proved by well ordering principle was that for any x greater than 7, that x can be written as a sum of 3s and 5s. That is, there are natural numbers starting with 0, y and z, such that x is equal to 3 times y plus 5 times z. Let's prove it by induction. So what is our predicate? Well, the predicate is everything after the for all and after the x greater than 7. There is y and z in n, such as n is equal to 3y plus 5z. And the base case is the first natural number that's greater than 7, so the base case is 8. So let's prove p of 8. 8 is equal to 3 plus 5, so we could pay 8 with one of the 3's and one of the 5's. Therefore, p of 8 holds. We found y, which is a 1, and a z, which is a 1. By induction hypothesis, now let's assume that p of k holds for an arbitrary k in n, which is greater than 7, which is greater than or equal to 8. That is, there are some y and z such that k equals 3y plus 5z. So now we need to show that under this assumption, p of k plus 1 holds. So we want to show that we could pay k plus 1 using some number of 3's and some number of 5's. And for that, we could crucially rely on the fact that we know how to pay k. So now it's a similar analysis to our well ordering principle proof. We want to construct the new y and the new z out of the original y, and z for the k. So if we have at least one of the 5s, then we could represent k plus 1 as k minus 5 plus 2 times 3. So our new y prime, will be original y for the k plus 2, and our z prime will be z minus 1. Great, in this case we found the y and we found the z. By existential generalization, there exist y prime and z prime such that k plus 1 is equal 3y prime plus 5z prime. But wait a moment, what happens if we don't have 5s? Well, in this case we'll need to think a little bit more. So in this case we only have the 3s. We know that our number is greater than 7, so we will have at least 3 of the 3s. Otherwise we wouldn't be able to make up a number greater than 7 without using any 5s. 9 would be the smallest number that's made out of only 3s, and that's greater than 7. Well, that's great, because now we can subtract the 3 of the 3s that we have, subtract 9, and put in 2 of the 5s, which is 10. So k plus 1 is equal k minus 9 plus 10, and we can construct the new y by taking the old y minus 3, and we construct the new z by setting it equal to 2. And we are done, because either we have 5s or we don't have 5s to make up k. In either case, we can construct a representation of k plus 1 as the sum of 3s and 5s. That finishes the proof of the induction step, and by induction we conclude that for every x that's greater than 7, x is equal 3y plus 5z for some y and z which are natural numbers.